Okay, so this is Chuang Gan. I'm a researcher from MIT IBM Lab. So it's very exciting to give this talk, as well as to introduce our team's efforts on multimodal learning from video. So Trinity Learning, it's end-to-end, has revolutionized many real-world applications, including, the traditional object detection, video recognition, machine translation, as well as speech recognition. And some of the recent systems actually even achieve performance that without a human. So on basis of this success, it's tempting for us to think that it might be deep learning already achieve human level intelligence. However, there are still several technical reasons for us to resist the temptation. First, deep learning algorithm we all know is very data hungry and require massive level data for model training. And secondly, it has a limited ability to adapt or generate to new concepts and new scenarios. So this system actually differs from human intelligence in terms of data efficiency, flexibilities, as well as the generalization. And here I will show a video, and we will see a baby. We will see how a baby is learning about the world. So it seems doing something a little bit random, bunching up together, making steps, knocking them down, and hearing the letters. So there might be a few things that her parent taught her before, but mostly he's exploring on his own. He can learn all of the science to figure out how things work. For example, he can associate how this cup look like with how it feel, and how it feel with how it sound. Essentially, he's building a causal model of the world to explain what has happened and infer what is about to happen, and then plan his action accordingly. So in this talk, I will introduce that how we can building the machine learning models that achieve the same, enable the same level of human-like learning. So in the first part, I will talk about audio-visual learning. So there's a lot of experience from cognitive science and development psychology that show that the human can naturally attend multi-sensory cue and their temporal coincidence to arrive a rich understanding of physical event and human activity. However, in AI, much more attention has been paid to how a single modality can drive learning. For example, if you look at today's computer vision system, mostly driving using visual signal. For example, we using image to do the image recognition. We using Kinetic YouTube, and we do the video classification. But what can sound give us? Okay, there's a lot of information that we can learn from that. For example, this example I want to give for them. If you watch these images, it might be hard for us to guess what's the material of this table. But when you hear the sound of physical interaction, so by hearing from the sound, you can easily infer that what it's made of. And also in the second images, when you first take a look at these images, you might think this child is in trouble and might need some help. But when you hear the sound, so you can hear he's laughing, and we know actually he's playing with the dog, and nothing need to be worried about. And sound will also allow us to localize objects that's out of our sight. For example, objects that are behind us or occluded. Here example. So by hearing the sound, you can predict that there's a train coming before you actually saw it. So inspired by the human ability on interpreting multi-sensory data, I would like to introduce a series of our team's work that leveraging the natural synchronization of visual and audio signal and enable AI system learn more from field data. So the first application I would like to introduce is called visual sound separation. So this is a joint work from Dr. Hang Zhao and Professor Anton Torba at MIT. We started working in this domain, I think, probably 3 years ago. And the problem we want to solve is that given a music performance video like this one, And our goal is to separate the sound source played by different musicians. So let's first have a quick review that how traditional audio-only approach performs this kind of sound source separation. So the model, what they will do, they will first estimate a mask for each sound component. And then they will multiply the mask on the input sound spectrogram to separate the sound source. The audio-only approach was worthwhile for some speech separation, but still hard to generate some many natural sounds, for example, music. So how to solve this problem? Our idea to solve this problem is to connect vision with sound by learning from music videos. So we believe that a machine can learn to associate the sound component with visual signal by listening and watching many music performance videos. So to this end, we first create a large-scale music performance data set, and it contains around 10,000 instrument video over a 20 instrument category. And we have made the dataset public available, and feel free to use that for research. So the core idea of our approach is first to create a synthetic training data by mixing arbitrary sound source from different video clips, like this one. And then the task of our model is to separate the audio track from the mixture conditional on their corresponding visual input. Even though the neural network is trained in a supervised fashion, but it does not require any label data. Therefore, the training pipeline can be considered as a self-supervised learning. And we also name the training procedure as mix and separate. A mix and separate framework is composed of a video analysis network, an audio analysis network, as well as an audio synthesizer network. And the video analysis network extracts the visual feature from video frame that contain musician playing instruments. And for the audio network, we first convert the raw waveform into sound spectrogram, and then using a unique style network architecture to encode the audio feature into different channels. The audio synthesizer network can then predict the sound by taking visual feature as well as the audio feature as input. The learning objective of this model is to estimate the mask. And we calculate the ground truth mask for each video by determining whether the target sound is the dominant component in the input mixture sound on the magnitude spectrogram. Finally, the predicted mask is thresholded and multiplied with the input complex sound spectrogram to get a predicted sound spectrogram. We further apply an inverse FTFT with the same transformation on the predicted sound spectrogram to reconstruct the waveform of separate sound. And in testing, we can either take the raw video frame as input to separate the sound, and we can also collect the pixel and take the region feature as input to hear the sound. Here I will show several cool demos, and this is the input video. So when we collecting the people of guitar, and imagine what you will hear. And how about we collect another instrument? And you might also be curious, how about I click the pixel of a background? For that, I click the pixel on bookshelf. What will happen? It's nothing. So this result indicated that our model can learn to localize the sound source and also separate its corresponding component. Here's another example. Again, when we click the piece of a trumpet. And also we can collect the piece of guitar. And And finally, we can also try click the background the wall and see if anything here. Okay, it seems pretty reasonable, a good result. And I will also show another cool application of music remixing. So essentially, our model can also enable us to do some sound editing in the video. And for example, you can do the volume adjustment for specified musician, or even remove the audio from a particular sound source. Here example. This is the input video, and we want to adjust the volume, make the left line, make the left line larger and the right line shorter. And of course, you can also do the reverse one. Okay, so even though this system achieve very impressive performance, but their approach are mostly built on appearance or later work using optical flow like motion feature representation, which has limited ability to find the correlation between audio signal and visual signal, especially when separating multiple instruments at the same time, like this example. So apparently in this very challenging case, the model did nothing. And to solve the problem, our idea is that to using human body language, which calls the music gesture that can provide strong visual condition to get sound source separation. So music gesture actually is a key point with structural visual representation. So our idea is that based on the key point coordinate change over time, we can implicitly capture the body and the finger movement of the musician when they perform the music. And using this kind of powerful representation, it could be possible that we can solve much challenging case. Here I will show some comparison result. So this is the video. So this is the result generated by a previous SOTA system named of sound motion, basically using optic flow like a feature. And clearly in this challenging case, he did nothing. How about our music gesture? Relying the body motion, what we can achieve? It's amazing that, even though the model not doing this separation, it's very perfect, but it's supposed, it's doing a reasonable good job in this challenging case. And here's another example. So again, the sound of motion system did nothing in this hard case. How about music gesture? So it also performed well. And the last one is a demo. Actually, I like most. That's about two people playing the do the piano. This is sound motion result. Again, they did nothing. How about our system? Okay, so we can this music gesture system actually using the implicitly human body model. It also opens up an opportunity to address even more challenging case that we can do the multiple instruments sound separation. Here you can see the demo. Okay, so you might be wondering that how we can understanding that how the key point what's the role of this key point played in this kind of music gesture system? To answer this question, we do some visualization of the key point of attention map, understanding what this model actually learned. So we have some very interesting observation. That we found that our model tend to focus more on the hand key point when it's separating guitar and the flute sound, while pay more attention to the elbow when they separate the cello and the violin. This really totally makes sense because this is the key point that really makes the sound when they're playing the music instrument. And the last time I would like to show is a musician that he's making two different sounds using his body language. And our music gesture system can also separate the sound of upper and the lower body part. So here's the result. So till now, you have seen that how something human can benefit, visual sound separation. And you might be curious that, can we directly generate a piece of music according to the body body movement? So in a follow-up work, we definitely achieve this goal. So actually, this is music generation from video actually is a very challenging problem. To achieve this goal, that we first need to recognize the physical interaction between musician and instrument from video. And secondly, we also need an audio representation that respects the major music rules, so we can easily, so it can be easily predicted from vision. And finally, and also most important, we also need a strong model to associate the two modalities. And our idea to address the challenge is that we first find two key elements for a successful video to music generator. For the visual perception part, again, we extract key points from video frame to implicitly model the body part and hand movement. And for the music, we propose to use MIDI, the symbolic music representation. So you might be curious, because we are computer vision community, you might be curious what is the MIDI representation. So essentially, MIDI events are encoding timing and loudness information for each note event, such as note on, note off. So therefore, given a pair of data of body key points and the MIDI event, music generation from video can be posed as a motion to MIDI translation problem. So to achieve this goal, that we build a system like this one that given video, we first do the key point detection using alpha pose and open pose, and then run graph network and detect the key point to capture human body motion. And then we're using a transformer to align the key point feature with the MIDI event. And finally, the MIDI event can be converted to waveform using a standard audio synthesizer. Here we can experience some music generation results. So since the MIDI representation are fully interpretable and transparent, so it will enable us to perform music style editing easily. Here I will show several cool demos. Here's another example. All right. So till now, I mean, in the first part of my talk, I mainly talk about how, and basically it's audio and the visual modality, that how they can benefit each other to do some cool application. I mean, so for the video understanding. So in the second part, I will talk about, I mean, so another multimodal modality that also a lot of researchers talk that about vision and language. And I mean, I think most people that are very familiar, I mean, for task, for example, is the visual question answering. That given images and natural question about images, and the VQA task is trying to predict accurate natural language answers. So in recent years, the computer vision community has made tremendous progress to track this kind of visual reasoning problem. Even though very impressive as the accuracy growth, it's still like I'm likely to get to know that whether this model undertaking a grounding visual reasoning or just leveraging the correlation in the training data. So in a recent year, that to mitigate the issue, Justin Jensen that proposed a synthetic visual reasoning data set called Image Clever to diagnose the visual reasoning abilities. The data set contains some synthetic images with composition attributes, including color, material, shape, and size. So unlike the VQA image data set, so Clever doesn't have the complex real-world visual scene or natural question, but the complexity or difficulty of the data set mainly comes from the composition no object attribute logic. And for most of the visual reasoning framework that it's very in the computer vision community, that what we would like to do is that we always using a magic pilot box. It's always called Unplanned neural network. It's always taking images and take a question using two different encoder and also reason module to predict the answer to question. And recently also there are some transformer network also to very good performance. However, so a basic question, we aim to understanding that in this kind of either untrained transformer or some, previous sequence model, there are two things that are trying to couple together. The first thing is about learning the concept, for example, what the meaning of the right. And second is the ability to do reasoning, for example, the functionality of counting objects. So in a set end-to-end design, concept learning and the visual reasoning actually are entangled with each other. So it's really different from what we humans do this kind of visual reasoning task. So first, take a look how human might perform this task. So when the person reads the question, are there an equal number of large things and middle spheres? So what we will do is that we will first identify all the large objects from images and count the number. And then we will perform the same operation on all the middle sphere and count. Okay, there are also a 3 middle sphere. A 3 middle spheres. And then we compare the two numbers we counted and generating an answer. So in this loop, that we can see that the human reasoning can be separated to 3 distinct components. First of all, visual perception, understanding what the scene is about, and then doing the question understanding, and finally they will do the logical reasoning. So inspired by this kind of human reasoning ability that we introduce a self-line of framework that we call it as a neurosymbolic visual reasoning. So this is the first work that joined with Ke-Xin Yi, that was student and mentor at Harvard Physics Department. So the basic idea of this model actually is very simple. That our model actually is really inspired from the previous how human reason from these images. So it combines the visual perception, question understanding, and logical reasoning. So concretely, that given input images, our model first perceives it with the neural synthesizer, or we can run basically it's actually using mask assistant to decide all the objects in the scene and output their segments. And also we will iterate, and we also apply an attribute network that to iterate the single object level attribute, including color, shape, material, size, as well as the 3D location and from the proposed segment. And the object attribute from this object representation of the scene can be used as a knowledge base for the reasoning task. And to understand the question, we're also using a neural semantic parser to turn the question into the function program. And then the model will perform logical reasoning via symbolic program executor. That is, the executor implement the logic of the program and implicitly write on the scene representation. For the main example, the scene representation is sent to the first module, filter the shape cylinder, which will find out the output all the cylinders from the scene. And the output from the first module will then send to the next module and return another list of filter objects. And the process will continue until the executor hits the final token, which will output the answer to the question. So in this process, our reasoning and perception is doing an implicit domain. Even though sometimes it will fail, but we can easily diagnose why they make mistake. And of course, this model offer several benefits. For example, we find that incorporating kind of symbolic structure as prior knowledge, we can almost solve this kind of challenging visual reasoning task. That we can achieve 99.8 accuracy in the challenging visual reasoning task. It almost solve all the questions in this data set. And also, our model is very data efficiency, since question understanding and isolation is the disentangle component of this whole pipeline. So our model only requires less question for training. And we can achieve around 90% accuracy only using 1% of training question. This is truly amazing. And also we can already achieve 99.7 accuracy only using 10% question. So this is both significantly outperforms some strong baseline using end-to-end trained neural network. And last and most importantly, because the symbolic program is fully interpretable and transparent, and we can easily diagnose its execution type, that we can understanding whether the longer model fail or visual perception model or the logical reasoning is not good. So everything is detangled that we can easily diagnose. And also this example that we can quantitatively evaluate how the program accuracy. So since all the image reasoning data set is similar, we also because there's a video workshop. And another question that, can we extend this idea to the video understanding? So take this video example as example. Take this video demo as example. When humans look at the video shown here, not only we can describe the event that happened, but we can also reason about the causal structure behind the event and making prediction about the future and even some observed counterfactual scenario. And what we believe that a smart AI system should not only solve the pattern recognition problem, but most importantly, it has the ability to capture the cause and effect in the physical world. So this is what I'm thinking also very important for the next step of video reasoning. So to this end, in collaboration with MIT, Harvard, DeepMind, and we built a new video understanding dataset called Clever, collision event for video representation and reasoning. And we hope to push the boundary of temporal and causal reasoning on video. So this Clever dataset is considered around 20,000 synthetic video and around 500,000 questions with well-controlled bias. We also provide the ground truth annotation for the video state for model diagnosis. And the question includes 5 different types of tasks and focus on temporal and causal reasoning, including descriptive, explanatory, predictive, and counterfactual. And we try to simplify the visual perception task that you can see that the scenario is only a few cubes that can that are collided. So the visual perception is really not hard in this sense, but the most challenging part is about temporal and dynamic. So among this type question, descriptive question trying to ask the agent about the event that happened during the video. So then what's the material of the last object to collide with the sine cylinder? So the answer will be the metal. The second explanatory question trying to ask the model to explain, the cause of a specified event. by choosing another event or object that is responsible to this collision. For example, in this example, the collision between the rubber sphere and the sand cylinder pushed the cylinder to make another collision with the metal cylinder. So therefore, we can regarding the second collision to be caused by the first. So the answer should be the second one. So the predictive question query about a future event after the video terminates. So in this example, the meteor sphere will keep moving along the white arrow and collide with the red sphere. So the answer will be the red sphere will collide with the meteor sphere. So the most challenging question in the data set is named the counterfactual question. So it requires the model to imagine an outcome when one object is removed from the scene and select the event that will happen under this unobserved scenarios. For example, we can ask, what will happen without the sand cylinder? The answer should be the second one. The red rubber sphere and the gray object they collide each other. So we do we evaluate a bunch of wide range of baseline model, including many state-of-the-art video question answering model, and also we adapt some awesome model on image reasoning data side, and we found that all of them perform very poorly. So even the for the match network, it achieve about 85 accuracy on the perceptual question, but actually it doesn't work well in some explanatory counterfactual predictive question. So this means that to work well in the data set, we really need the reason the system to understanding dynamic and causal structure, and counter AI system fall short on this one. So to address this problem, and we design a new model called as the Neurosymbolic Dynamic Reasoner, which is using the structural, visual, and long representation, and to solve the challenging causal visual reasoning task. So our idea is also very simple. At first, we take the video and pass them to an object-centered representation that basically detects all the object simultaneous mask. And also, it tries the attribute feature, including attributes of color and shape of object, and also their their coordinate. And then we will send this representation to a dynamic model that can be and can be used to predict the object trajectory across different frames. So the dynamic work has a good generalization that to attend to different object combination, and can reasonably good to understanding to handling what will happen next, and also what might happen in some counterfactual scenario. And the input question will pass into a program that representing the underlying logic by the system-to-system network. And finally, the program will execute it on a symbolic executor on the predicted motion trajectory of the answer. So here I will show an example of how this model performs the counterfactual reasoning. Here the upper video shows the input video. The upper and the upper is input video, and the lower video shows the predicted trajectory when the sand cylinder is removed. So you can see that our model can capture the counterfactual event without the observation and answer the question. It's quite accurately. And we also do some quantitative evaluation, and we find that our model is better on some challenging explanatory predictive and counterfactual question that will achieve reasonable good performance. So this result demonstrates the potential of this kind of neurosymbolic approach that incorporates the ability of understanding the visual scene and the underlying causal structure aspect of language. So our data set and code is publicly available, and feel free to use that one. And we also run a challenging, a current challenging on IDCV this year. And some more detail you can check about the visual dynamic workshop on ICCV. So what's the next? So about the video understanding. So a long-standing goal of AI as far as in communication is we are trying to engineer motion agents that can interact with the world, whether assist around the house or in outer space. So such AI system must learn to perceive and then reason about the physical work around them in order to manipulate objects and formulate the plan to execute the task. But a major challenge is to how we can develop developing and benchmarking such agents. In a quantitative way, right? So since the training robot and also the model, since the training model with real robots very expensive and involves some safety risks. So we have built a world simulator named as the 3D world that in short is TW that can enable simulation of high fidelity multi-sensor data and the physical interaction between mobile agent and object in a photo and physical realistic 3D environment. So this is a demo that we can show that TW can support real-time near photorealistic image rendering and also believable physical interaction for a wide range of material types, including clothes, liquid, deformable objects. And most importantly, that it also supports multi-sensory input that so that we can do impact sound simulation. Here example. So this platform will also open up a new opportunity for us to define a new embodied AI task that for video understanding that we can put an agent in a both photo and physical realistic environment. For example, in this year on the CPR embodied AI workshop, we host a TW transport challenge. So as shown in the demo, robot agent with a 6-degree articulated arm is required to find a small number of objects and scattered around the house, pick them up, and transport them to the desired final locations. To complete the task, the robot agent must plan a sequence of action to change the state of a large number of objects in face of realistic in face of the realistic physical constraint. So we believe this work simulator can really benefit the whole community of video understanding that and empower researchers to develop more intelligence. Either for physical understanding or building robots that can add in the physical world. So this platform also publicly available on the website, and feel free to use them. Okay, so I would like to